Okay, so we have started recording, and as I was mentioning that people who had done BEM in their autumn semester would have had some introduction to beams. Nevertheless, for the benefit of everyone, we will go through the basics of beam, just a fair idea, just to get a fair idea of what beams is. Now, without going into too formal a definition, we will say that beams are the kind of members which are slender, so they are quite thin with respect to their length. Usually they have an unchanging cross section along their length, and usually when we talk about beams, we understand that the loading on the beams is taking place perpendicular to the longitudinal axis of the beam. Okay, so these are certain important things that we keep in mind when discussing beams. Now, before we go into the mathematical description and the problem solving, I want you to spend a minute to just give me some examples from your day-to-day life, which covers or which are like examples of beams. Can you give me an example? I will start with the first example, which is literally the beams that you find in your roofs. So whether it's one of those traditional roof structures which are less and less common in India, but more commonly in the reinforced concrete buildings that most of us live in, work in, you will see that if you just look at the ceiling, unless you have a very sophisticated false ceiling which covers all these internal structures, if you live in a normal house, okay, very normal house, then if you look at the ceiling, you will find that near the walls or where the wall meets the roof, or perhaps even in the middle of the ceiling also, you will see certain rectangular type things projecting out of the ceiling. Okay, so because everything is painted in the same color, it does not look anything different. But if you have actually ever seen a building being constructed, you will have noticed that first you will have the construction of the pillars, and then they will set up certain horizontal kind of structures which are relatively slender and which look almost like pillars, but they are horizontally placed over the pillars. And it is across those horizontal members, these are called the beams, that the ceilings are made. So if it's a multi-story building, the different floors are basically first built using these kinds of beams, and the floors are laid down on these beams. It's a similar kind of thing that goes on while building bridges. So you have some kind of scaffolding structures which are like the skeleton of the bridge, and the road-like things which we actually travel on, they are laid down later after that underlying structure is laid down. Okay, and that underlying structure is again in the form of these pillars and beams. Now, going beyond these very classical engineering examples, can you please tell me some other examples which are like beams?
So Eiffel Tower and mobile towers.
Eiffel Tower, right. So Eiffel Tower is probably a better example of a truss-like structure. But you are right in thinking that even there you certainly have some horizontal members which do carry loads, and on which the loading is perpendicular to the longitudinal axis of the members. So yes, in Eiffel Tower also you will have certain members which are like beams. Anything beyond these things? I could not hear.
Sir, shelves where we put books, etc.
So even the bed, the wooden structure.
The bed, right? Yeah, so if you have a wooden bed, very classical wooden bed, you will see that there are certain horizontal things over which the mattress is laid. But there was some example before
Sir,
the bed.
Sir, like I saw this in some YouTube video that like our hand is also actually like a beam,
Very
hand and legs.
Yes, yes. So when you are standing, your leg, the bones of your leg, they act like columns. Okay, they are more like pillars. But a hand is a very good example. The well, when you say hand, if you say like the individual bones, then yes, they are like the beams. For example, when you are working on your laptop or on your computer and you rest your arms on the table and maybe put some weight, the weight of your shoulder and the upper part of your body on them, so it is very much like a beam, very sophisticated kind of beam. Any other example?
Sir,
So
curtain.
basketball.
Guys, can you speak a little bit lower? The voice is breaking up here.
Sir, curtain rods.
Jay Marothia, I simply cannot hear you. Maybe you can write in the meeting chat.
Okay.
Your voice is completely breaking up. Maybe you can write in the meeting chat. Jay Marothia. Anyone else?
So a folding
Curtain
study
rods.
chair.
What?
Curtain rods.
Curtain rods. Very good. Very good example. I like this.
So a folding study chair.
Folding study chair. So don't say folding study chair. You say the horizontal members that are present in the.
Yes, sir.
Yeah. You have to be a little
The
bit
board.
specific. What?
In the board, we have this horizontal like.
Right. Exactly. Jay Marothi is saying swings horizontal rod. Very good example. Very good, Jay Marothi. So something from the playground. And actually in the playground, you will have multiple such examples. So recently Olympics were held. So take your mind back to the Olympics if you have seen some of those videos. So in gymnastics, you have the horizontal bars, which are very difficult. Okay, but when the gymnast is swinging on them, you have the horizontal bars as a classical example of a beam. Then Kirti is saying basketball goal, the L-shaped structure on which the basketball hoop is mounted. The L-shaped structure, the horizontal part of that L-shaped structure, yes. There is very much, there is almost like a cantilever beam.
The weightlifting board.
Absolutely. The horizontal, yeah, that's a very classical. In fact, it's so classic an example that in certain textbooks they will give that example as a motivating thing in the first page of the chapter. There was some other example that was given. Optical bench. What is optical bench? Ayashkant Mishra. What is optical bench?
Sir, we mount lens onto them to, determine their focal length and test their properties.
Okay. Yes. That is not a day-to-day life example, but yeah, it's a correct example. Pull-up bars, certainly, they are very much like the horizontal bars in gymnastics. Yeah, normal bench, Niranjan, thank you. So we are thinking about so sophisticated examples. The normal bench that you find in your schools, why schools, even in our homes, that's very much that horizontal part of the bench. That's a very much an example of a beam. Kirti is saying, are frames of eyeglasses examples of beams too? Well, the nose bridge. Okay, so the little horizontal part which is connecting the two eye lenses, that may be thought of as a beam. Yes, railway tracks are examples of beams, but they're very special kinds of beams which are considered to be laid on elastic foundations. In fact, when you go on to higher classes, and if you ever take a class on advanced mechanics of solids, you will find that this is a very important example to study, and the analysis is not so simple. So the kind of things that we'll be studying in these 2 weeks, that will not be sufficient to address how you model railway tracks. Okay, it is the theory of beams will have to go much beyond the second year level to be able to model railway tracks. Rods for holding on to buses. Yes, rods for holding on to buses in bus. Why just buses? Like local trains also. Yes, Apurv, I understood the optical bends thing. Okay, so we have certain motivating examples, very good examples. One example which you guys have not given and which is very understandable. Arshdeep is saying cricket bails placed over wickets. Yeah, yeah. So one example which you have not given is that the horizontal bar which you find in your bicycles. So had you been in the campus, that would have been the first example that would have come to your mind. But unfortunately, you're not in the campus, you're not riding bicycles every day, all the day. So that example did not come to your mind. Anyway, so we proceed with the theory of beams. Okay. Now, as with our previous approach, we will be taking a very utilitarian kind of approach, meaning that the theory of beams, it has been developed for now, I think more than 200 years.
Sir,
Okay. Yes.
Sir, but that horizontal bar in cycles is not present in some of the bicycle models.
In the ladies' bicycles, it is not.
Yes, sir. So why is it like that? Like,
what do you mean? Why is it like that?
so I mean, like you told that the horizontal bar is an example of beam, so
Yes,
that means it should be present in all the.
No, wherever the horizontal bar is there it is an example of a beam. Where the horizontal bar is not there, it doesn't even exist. So it is not an example. So it is not an absolutely essential member, but it's good for the structure. But I mean, as in every place of engineering, there is always a compromise between requirement and optimality. Okay, so if you want to sell bicycles in India, where you have to target the female population, where a lot of them do not wear jeans, unlike the people in our age and certainly in your generation also. Early generations, they used to ride bicycles using saris. When you come to Kharagpur, you will see that many of the ladies here, many of the lady professors also, they ride bicycles wearing saris. So we go to the theory of beams, and the first thing that you have to understand is the shear force and the bending moment. So what is the shear force and bending moment? Now you see, earlier in your first year, you have talked about axial loading of beams or axial loading of members, and then in our previous chapter we have been talking about torsion. Now, what is the commonality between this, the axial loading and the torsion chapter? The commonality is that when we are talking about the stresses that are generated, we are actually always making some cut sections through the members of interest, and then we are trying to analyze what are the internal forces that are generated in response to the external loading. Whether it was in axial loading, we used to load it axially and then cut the member and then see what is going on inside it at different cross sections. Similarly, in torsion also we did the same thing. Some kind of twisting load was applied on the shaft, and then we cut it at various sections, and then we saw what is going on internally. The spirit is the same here. So whenever we have a beam and whenever we have external loadings being applied to it, we are interested in finding what is happening internally to the beam at various cross sections. This is the heart and soul that you have to understand. Like, this is the ultimate motivating thing. Okay, at different cross sections of the beam, what is happening? Now, when you have to address these things, there are certain challenges to it. Okay, and that is where we'll go to the writing app and try to see what is going on. So, in the bending of beams, so going to a little bit of classification for the sake of completeness, what we'll say is that beams usually come in these sorts of fashion. So it's important to understand this. So this is just knowledge. Okay, there is nothing really to understand. You have a beam like this, which is usually represented in the front view like this. On the left hand, you have a pin joint, either left hand or the right hand side. And on the other one, you have a roller joint. And this thing was actually covered in your first year basic engineering mechanics, that this kind of a structure under any kind of loading. Okay, suppose you have a loading like this, or maybe a distributed loading. So I will not depict the loading right now. So this is referred to as a simply supported beam. You have a hinge joint here, you have a hinge joint here also, but the lateral motion or the horizontal motion of this pin joint is not constrained here. It is free to move horizontally here. So this is referred to as a simply supported beam. We have another example, very classical example, a cantilever beam. So a cantilever beam, the typical way that it is made up is that you have a wall which is represented by this hatched line. This beam is firmly fixed to this wall, either through some clamps here, or a slight portion of this wall is excavated and or dug out, and this beam is inserted into that wall, and then cement is put here, and so it is firmly fixed. Okay, there can be different ways of firmly fixing a beam to a wall, but the other end of it is completely free. There is no roller joint, there is no pin joint, no nothing is there. Okay, so this is a cantilever. What did I write? Sorry. This is a cantilever beam. One of the most common examples of beams everywhere in the world. And then you have another example, which is a slight variation on these two things, which is referred to as an overhanging beam, which is also fairly common. Okay, so there is a part of the beam which is hanging beyond one of these simple supports, so it is referred to as an overhanging beam. Right, so all of these three examples, they are what are categorized as statically indeterminate beams, or not categorized, I would say they fall under the category of statically determinate beams. However, you can have examples of statically indeterminate beams also. For instance, you take this example itself. You take this example itself, but slightly modify it in this fashion, that you add another roller joint here. So you will see that the number of unknowns that are present here. Okay, so how many unknowns will be present here in terms of the reaction forces? Quickly tell me.
4.
Very good. So, and this is basically a 2D problem. So you'll have three equations, two force equations and one moment equation, or one force equation, two moment equations, things like that. And you will have 4 unknowns. So this is statically indeterminate. Another example could be you have this cantilever beam. Let me just redraw it quickly. You have this cantilever beam. All right, but now you want to support it in an extra fashion like this. So how many unknowns are here now?
4.
3.
Yes, 4. So you have the horizontal unknown reaction force here, the vertical unknown reaction force here, and an unknown moment also here. So whenever there is a built-in end, you will also have an unknown moment. So 3 unknowns are present here. In addition to that, there will be a horizontal resisting, a vertical reaction force here. Okay, a vertical reaction. You will not have any horizontal reaction force here because there is no resistance to the horizontal movement of this end of the beam because of the presence of the rollers. Okay, so this is very much a revision from your BM. Nevertheless, in the context of beams, I want to re-emphasize it. Okay, so this is also a statically indeterminate thing because you have 3 equations as usual, but you have 4 unknowns. You can have further examples of this. For example, you can have a structure which is like this, which is built in, a beam which is built in at both the ends. So how many unknowns are here?
6.
6. Very good. So all of these fall under the category of statically indeterminate beams. And please do not think that these are only the 3 examples of statically indeterminate beams. Okay, you can have many more examples, okay, of statically indeterminate beams. But usually statically determinate beams, they usually fall under these categories. Of course, you can have slight variations on these, and many examples of this you will see in the problem sheet, in the tutorial sheet. So without any further ado, let us try to go directly into the shear force and the bending moment things. All right. So shear force and bending moment. What are we talking about? Shear force and bending moment. Well, you see, earlier when we talked about the axial loading of beams or the torsion of beams, we were only thinking about only one kind of resisting forces or resistances internally. But when we're talking about beams, you will see that in addition to a force, there will also arise a moment internally. What am I talking about? Let's take an example. Suppose we have a beam like this. Suppose we have a beam like this, and some kind of loading is present. So please note that when I draw this kind of a horizontal line with downward pointing arrows, it basically means that there is some kind of a distributed load here. This distributed load usually is expressed in terms of a force per unit length. So W is the force per unit length, having the unit of Newton per meter. In addition to this, you can have a concentrated force also acting somewhere. And let's say that this is a simply supported beam. A classical example. Now, the first order of business in order to understand what is going on internally in this thing is to consider the free body diagram of this thing and to consider the reaction forces which are arising. And we will take up like very definite examples to solve these things. But right now I don't want to solve. Okay, let's say this force is P. I don't want to spend any time on actually finding out the expressions of the internal forces at this end and this end. But we know that it can be done because this problem is statically determinate. What I'm more interested in finding out or in highlighting to you is to take a cut section like this and to illustrate to you that if you focus your attention on the left part of this section, of this cut section, you will see something like this. If you draw the free body diagram, you will see something like this. Of course, you have the loading present here like this. You will have some kind of a vertical reaction force, let's say some RV. Okay, you will eventually find out that the RH will be 0, but for the sake of completeness, let's write it. It will come out to be 0. Okay. Now, what is happening on this end? Okay, so you can very well, in fact, intuitively understand without doing any maths that there will be some kind of a vertical reaction force which is exerted by the right side of the cut section of this beam on the left hand side, which we are considering. I repeat, there will be a reaction force which is being experienced on this cross section. That force is being exerted by what? That is exerted by the right hand side of this orange colored cut section on the left hand side, which we are considering. Question is, how do we depict it? There is a standard conventionally accepted procedure or method of depicting it. So what I mean to say is that you may depict it like this, or you may depict it like this. So the standard accepted convention is to take this one. There is absolutely no mistake if you take this one, but please do not take it. Okay, so everyone from now on, you take this kind of a downward pointing force as the reaction force. This reaction force is what is referred to as the shear force, because you can see that this is grazing along this surface. Okay, this is just adjacent to this surface along this surface. So this is referred to as V. This letter V, again, there is nothing holy about it. It is just that in almost every textbook you will find that the letter V is used to represent the shear force. Okay, it's just like in physics. The charge, it is almost always represented by small q or capital Q, electric field by capital E, voltage by V. So things like that. Okay, so the V is used to represent the shear force. However, I said that the V is used to represent the shear force with a downward pointing arrow. That is true only for this kind of a cross section where you are considering the internal cross section or the cross section to be present on the right hand side of the body or the member. Which is, what I mean to say here is that suppose instead of the left part of this orange colored cut section, you had taken the right hand part. Suppose you had taken the right hand part, then the convention is to take the opposite one. And that makes sense because if on the left hand side you take the downward thing, definitely on the right hand side it must be the opposite way. And again it is represented by this V. Okay, so this is the correct convention. So you take this one for the left hand part and the upward pointing arrow for the right hand part. All right. Now, in addition to this, you will find that in order to maintain the static equilibrium of either of this one or of this one, it is not enough. So I must draw this thing completely. So let's say this is RV1 and this is RV2. And there is certainly no horizontal here. Okay, there is no RH2 here. You will find that the force balance will be maintained by this V, but the moment balance will be maintained only if you consider an actual internal moment, which is referred to as the bending moment. So on this cross section also, on the left hand side of the cross section, you will find there will be an internal bending moment, which is represented by this kind of an arrow. And here also you will find that this is by this curved line. Okay, this curved line and this curved line. Now the convention is that you consider this anti-clockwise thing to be the bending moment for this left part, and for this right hand part you take this clockwise. Okay. Now you may be thinking that what kind of, are we doing politics, or are we studying law that we are taking these accepted conventions? So these seem to be completely arbitrary, and yes, they are arbitrary choices, but they do have certain basis and certain connections with the underlying distribution of stresses, and which we will study in the next week. Okay, so for right now, you be satisfied with this. I can go into the depth of it, but I don't want. What I want to do right now is to say to you that accept on good faith these accepted conventions, and using this, let us try to look at a few examples of how we can understand the distribution of the shear force and the bending moment for different kinds of standard situations. They will be useful certainly for exams, but they will also be extremely useful in a professional environment. That is because the first step in designing beams. Okay, so as a good engineer, you will always be expected to design things from the perspective of designing of beams. One of the first things which you have to do is to get an idea about the potential distribution of the shear forces and the bending moments internally in the beams. Okay, so let me illustrate the concepts to you through some examples. These are not like problems, rather these are almost like theory. Okay, but you will see that we have to, we have to do it almost like a problem. So first example is this. Very standard example. I think this is also present in Beer and Johnson for the simple reason that it is one of the most standard examples. Okay, so we have this kind of a simply supported beam where the loading is via a concentrated force acting exactly at the mid span of the beam. Okay, the entire length of the beam is L. The entire length of the beam is L, and this force, let's call it force P, it is acting at x equal to L by 2, where x is of course at the left end. Okay, so this is L by 2. So how do we go about drawing the shear force and the bending moment diagrams? So when we say shear force and bending moment diagrams, what is the diagram about? The diagram is basically a plot of the shear force as we move from the left to the right of the cross section, or the left to the right of the beam. So what we basically mean is that you take different kinds of cross sections here, 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 and here. So as you move along the length of the beam from the left to the right, taking different such cross sections, what will be the values of the shear force at different cross sections? So if you plot it, so it is something like this, that you plot, you consider a horizontal axis like this horizontal axis, where the left end, the 0, is this left end, and the right end is at L, and then the vertical axis, it represents the V. So the value of the V as you go from 0 to L, that is referred to as the shear force diagram, SFD. Okay, similarly, you will have the BMD. BMD means bending moment diagram. And you will see that in the tutorial sheet that I have shared with you, all the problems involve asked to find out the shear force and the bending moment diagrams. Sometimes in short, they are referred to as the shear diagram and the moment diagram. Same thing. Okay, so your job in all of these problems will be to find out the correct distribution of the shear force and the bending moment as you go from the left end of the beam to the right end of the beam. All right. How do we go about doing that systematically? The first step is to find out the reaction forces at the left end and the right end. Without that, you cannot draw a complete free body diagram. Now, I will not go into the trivial details of that, because for a very straightforward situation like this, you can immediately understand that because it is this force is very symmetrically loaded at x equal to L by 2, the force at the left end will be P by 2 and the force at the right end will be P by 2. Okay, so let us not unnecessarily drag on these easy things. I can quickly go from here to here and write that this is P by 2 and this is P by 2. Easy enough. Now comes the interesting thing. We take a cut section like this. We take a cut section like this and we consider the left part. The left part will look like this. As simple as that. We should not forget this force P by 2. Now we have to represent the internal forces. For the internal force or the internal resistances, this will be the shear force, this will be the bending moment. Because we have already accepted this convention, we'll proceed like this. So when we have this thing, what we are basically doing here is to consider an x. We're considering an x which is between 0 and L by 2. Okay, you can consider this to be x equal to 0 also. Okay, but usually it is not done because there is a case of at x equal to 0 you have this p by 2. So there is, very theoretically speaking, there is a slight problem of continuity there. So we will stay within this 0 and L by 2 without going to the equality sign. Now here you tell me what is the force balance. Tell me what is the force balance here.
P equals to P by 2.
Yes. So it is like this, that usually you write it properly, that V minus P by 2 is equal to 0. Then V is equal to P by 2. I'm writing like this because in some of the more complicated situations, it makes sense to write like this. Otherwise, I find that there is a sign. I always make a sign mistake. Okay, so I make it a practice to write it very formally like this. Regarding M, how do you find out M?
M is equals to Vx.
No. You have to be very careful like this. So you do like this. See, M, what you said, M is equal to Vx is fine, but what you do?
So we have to also assume P by 2 in
Listen. If you follow this method, what I'm going to tell you, there won't be any mistake. Okay. So this M is on the right hand side of this, whatever this portion you are considering, right? It is on the right hand side. And on the right hand side only this V is there. Okay. So what you do is you consider an axis, or you find out the moment about an axis which is passing through this end only. Okay, this right end. On the right end, you take an axis and you consider the bending moment about that axis. So the contribution will be from this P by 2 and the contribution from this V will be 0. Okay. Furthermore, you can also think of it like this, that you are writing this equation, basically the entire moment equation, sigma M. So maybe you are considering something like mz equal to 0, something like that. Okay. So please note that this M is not this M. Okay. This is the generic M from your first year BM. So sigma M is equal to 0. And what we'll do is we'll consider the anti-clockwise to be positive. With this understanding, we can write from here that M minus P by 2 times what? Tell me.
X.
X. Very good. So X means we are considering this much to be X. Okay, our X 0 is here. This is X equal to 0. Okay, so this much is also X. So P by 2 into X, that is the moment contribution taken about an axis which is passing through this end. All right. Now this is equal to 0. So M is equal to P by 2x. This is almost like a brainless example, but it's good to see from the very simple things. Now you tell me, if we go to this other zone, okay, that when we go to L by 2 less than x L, we have to take a cut section like this. And there, for that, our diagram, our free body diagram will look like this. You have the P by 2 here. You also have the P force present here. This entire distance is x. This is L by 2. Furthermore, you will also again have a V here and a M here. So now for Just give me a second. Okay, now you tell me what happens for x less than L greater than L by 2. The force equation.
Sir, P plus V equal to P by 2.
V plus P minus P by 2 equal to 0. Is it not?
Yes, sir.
So V is equal to what?
Minus P.
Minus P by 2. Good. Next for the M, tell me. Same kind of thing, okay? Sigma M equal to 0, anti-clockwise positive. So first
We can
M minus P by 2 into X minus P into X minus L by 2.
This is, so now we'll have plus, right?
yes, sir.
Yes, sir, plus.
Plus P into X minus L by 2.
L by 2.
Yeah, L by 2.
Fine. So this contribution comes from this downward pointing external force. Okay, the moment arm is this much. Okay, for this one, this is the moment arm. This is X minus L by 2. So this is equal to 0. So how much is this value? Tell me.
P by 2 into X minus L.
P by 2 into
X minus L. X plus L.
L minus X.
L minus X, no? Because you have to go to the other side, no? This is on the left hand side. All right. Now you tell me what the diagram here will look like. So see, 0 less than X less than L by 2, you have a constant value of V, that is P by 2. So this is P by 2. Okay, this is P by 2. Let's say this is L by 2. Okay, this much is this is L by 2. Beyond L by 2, what is the value of V? This is minus P by 2. So you have something like this. Okay, and you understand that just like in calculus, we used to draw the like a piecewise continuous function like this with a dotted line. We used to do the same thing here. Okay, you see there is a discontinuity here at x equal to L by 2. Okay,
So actually,
yeah, tell me.
So generally we take upper side as a positive and lower side as a negative, no? Means in vertical above side.
Yeah, but you are taking the downward pointing V as the positive here, no? That's why it's coming like this.
Okay, sir. But sir, suppose if someone takes a reverse of it, so diagram will look like reflection.
Diagram will look opposite, but that is why, I mean, worldwide, this is the accepted convention. So even if without mentioning anything else, you just draw the shear force diagram like this, people will understand what you are doing. Okay, so this is like the accepted code within the among engineers. Okay, many engineers follow this convention.
Really, that sign matters in daily life. If we give only the magnitude, will not work.
No. What I'm saying is that what you would be doing is not incorrect, but in order for effective and easy communication among different sets of engineers, see, when you are building something, you are not the only engineer working on that project. There'll be a bunch of engineers working on that project. So if you choose to do something because of your sweet will, someone else does something like this, people will waste a lot of time trying to understand what he meant and what she meant. That is why these kinds of things are done, so that everyone follows the same kind of things.
Yes, sir.
But I'm saying that if you take the opposite kind of thing, it will be absolutely not mathematically incorrect. Okay, nobody can give you a mistake, but please don't do it. Okay, please don't.
Okay.
Yeah.
Sir?
Yes.
We have considered the portion after P to be X method, but you have taken starting from the left side as x.
I did not understand what you were saying. Can you say that again?
Sir, x is lying between L by 2 to L, sir.
Yes.
So after P, we should take x, na, sir.
After P, we should take X.
Yes. Because
No, I am not taking X to be 0 after P. X is always 0 here.
yes, sir.
Yeah, so
I was just confused by this distances part, sir. As x is lying between L by 2 to L, we have to take x from P, I'm thinking, sir, but you have took it from the leftmost end.
I think we are maybe talking at cross purposes. You think about it a little bit. Okay, so if there is any other persisting confusion, you please post in the discussion channel. Right now, I don't think I'm getting across to you. Okay, but please do not sweep it under the carpet. If there is any confusion in your mind, please do take it up within the discussion channel. I'll try to clarify it. Okay, but I do want to go to another example in the remaining time we have, so that okay, we don't fall behind. But before we do that, the same kind of thing I wish to do for this m. You please tell me, looking at this 0x x lying between 0 and L by 2, this m is equal to p by 2 into x. Okay, so this is a linearly increasing thing, so it should be like this. What is the value, maximum value of this m here?
P into L by
P L by 2.
PL by
4.
4. PL by 4.
PL by 4.
What will be the remaining thing here? This is L by 2.
slope.
Yeah, negative slope. So the expression is p by 2 L minus x.
Sir, it will start from their point only.
It will start from that point only, because when you put x equal to L by 2 here, it becomes L by 2 together. This is PL by 4 again, same value as this. So there is no discontinuity for the m now. And when you take x to be equal to L, this entire thing becomes 0. So the bending moment at the right end is actually 0, which makes sense. So the slope here is the same as the slope here, because the slope here is this p by 2, the slope here is this minus p by 2, of course with the negative sign. So you basically have a diagram like this. Okay, these things are joined. So this is the shear force diagram, this is the bending moment diagram. Now quickly, I want to go to another example. This time we are going to take a cantilever beam. But unlike the previous example, we are going to consider a distributed force. Rather, it is a uniformly distributed force, meaning it's a constant value all along the length of the beam. This diagram is a little bit, off, but you understand that this is a perfectly horizontal line, okay? And the intensity of this force is W Newton per meter, okay? In terms of Newton per meter. So we want to find out the shear force and the bending moment diagram of this. The general procedure is exactly the same as before, except that we can pull off one little trick here. The little trick is that, and it makes sense with our procedure, that we are going to take our x from the left end. And if we take our x from the left end, we really do not need to find out the reaction forces on the right end. Because you are going to go from x, you are going to write the whole thing between 0 and L. The whole length here is L. This is the whole length. So when you go from x up to L, you are not actually reaching L, you are stopping just before L, kind of. So you don't really need to find out these reaction forces. Had the wall been present here and you would have started from x equal to 0, then you would have to do that. So how do you go about doing it? Well, you take a cut section like this, arbitrarily. You consider the section which is to the left of it. Sorry, can't seem to draw a horizontal line.
Sir, could you just please repeat once why we don't have to find the force on L, like on
right? So imagine that you are taking a cut section somewhere here. Okay, so when you are taking a cut section somewhere there, you have effectively reached L. Okay, you have effectively reached L, and your entire diagram is looking like this. Okay, so you can complete your diagram by drawing this kind of a thing. Finished. In fact, this V and this M that you are saying, that will actually, if you really want to find out the internal forces, the values of V and M that you get there, those will be equal to the internal resistances. But what I'm saying is that you don't really need to first find out the internal resistances like this and then go about solving the problem. Okay, because this generic thing that we are doing, taking the cut section at any distance x from the left end, if you ultimately in the expressions that you find for V and M, if you put x equal to L, the answers that you will find for V and M, they will be the answers to the internal this reaction forces or the reaction resistances there. That's all there is to it. Okay, I mean it works only for this simple kind of example. Okay, for other kinds, please don't think that I mean every time you have a cantilever beam like this, it will work like this. Okay, it may not, but is for a more complicated situation. Okay, so we draw the V and the M, and I don't think I'll be able to solve this problem, but I'll just take another 30 seconds or 45 seconds. So these are the internals, so these are in green, and the part of the distributed loading that we have to consider is over this length x. So please remember that this is length x. This much is x. So let's quickly finish the force balance. What is the force balance? Tell me.
W into X.
V plus W X plus
V plus W into X.
W
Okay,
into X.
yeah, please understand that this is plus. Okay, this is very, very important. Okay, so this is V plus W into X. W is the force per unit length. You have to multiply it by the length to get the entire force. So W into X has the unit of Newton. Okay, because W itself has the unit of Newton per meter. Many students make this mistake. So whenever you write these kinds of force balances or moment balances, please ensure that the units are matching properly. That should be your first check. So V is becoming equal to minus W into X. Okay, so you think about what is going to happen to the M, and tomorrow we'll finish it up. Okay, along with another example, and then we'll start solving the problems from the tutorial sheet. All right, I'm already at 11 o'clock. All of you, please go to the next class. Thank you. Bye bye.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.